Hey there folks, we're now in our next video in number theory, and here today we're going to talk about more in our chapter in the theory of congruences, and we're going to talk more about properties of congruences. So we have talked about some properties, some very basic properties in our first videos about it, but now we're going to expound it and some properties like the reflexive property, the symmetric property, and the like. Okay, so we state them all. Actually, there are six properties now that I will be presenting, and actually, I will also be proving them, and also will be citing some examples regarding this these properties. So let's state that formally in a form of a theorem. So this is theorem 3.2. Let m be greater than 1. Actually, this m is the modulo, our congruence modulo. Again, throughout our videos, I think I forgot to tell this before. Throughout our videos, all the letters rather, are assumed to be integers. Okay, all the letters are assumed to be integers, and all moduli, which is the plural for modulus, are assumed to be positive integers. So even though there is nothing that tells us that they are positive integers, it should be understood, um, given our chapter or given our subject. So let m be again the modulo be fixed, and a, b, c, and d be arbitrary integers. Then the following properties hold. So we have here again, like I said, we have six properties here. Starting from let's start first, or let's discuss first the first three. The first three properties here are the very basic ones. So we have the reflexive property, we have the symmetric property, and we have the transitive property. So for the reflexive property, just like in our properties inequality, we say that A is congruent to A mod M. Okay, by the reflexive property. Also, in the symmetric property, we say that if A is congruent to B mod M, then B is congruent to A mod M. That's symmetric property. And for the transitive property, if A is congruent to B mod M and B is congruent to C mod M, so therefore we say that A is congruent to C mod M. So this is very similar in our properties in equivalence. So the next four theorems will tackle a little bit more about the operational part of it rather than the equivalence properties, the second equivalence properties. But the 4, 5, 6 will tackle more of the fundamental operations. Okay, so we say for if A is congruent to B mod M and C is congruent to D mod M, then it is true that A plus C, this part here, plus this part is congruent to the second part plus the second part, mod M, provided they're still in the same modulo or modulus. And this does not only follow in addition, it also follows in multiplication. So A times C is congruent to B times D, still strictly in the same modulus. Okay, for number 5, it states that if A is congruent to B mod M, so there's no other congruence relation. But if A is congruent to B mod M, then if we have some certain C in the integers, A plus C is congruent to B plus C mod M. So we just simply add a same integer to both sides of the congruence, and then it will yield us to be congruent still. This doesn't only follow in addition, it also follows in multiplication. So A times C is congruent to B times C mod M. Okay, so if we are multiplying the same integer in both sides, for both sides of the congruence, it will give us still a congruence relation. That's for property 5. For property 6, if A is congruent to B mod M, then A raised to K is congruent to B raised to K mod M for all K in the positive integers. So we say that if two integers are congruent and then we're going to raise them in the same exponent, then it will still yield us a congruence relation. Okay, still a congruence relation. Okay, so those are the four or six properties that I have presented in Theorem 3.2. Again, they are additional properties of congruence, and in this part of the video, we will be proving all of them. Okay, so let's start with the proof. So proof. Okay, let's kind of rewatch or review the first three properties. Maybe you can pause the video and then try to copy them so that we will you won't need to or rewind the video so that you can see the value. I will be having my copy here on my own. So kindly have a copy of your own. Maybe you can have a screenshot or the like. One, two, three. Okay. And then I'm going to also show you the properties of 4 to 6. Okay, so this is property 4 to 6. Actually, it includes 3 here. So kindly have a copy. You can pause the video to copy or maybe have a screenshot so that you'll have a copy of your own. One, two, three. Okay, so let's answer now for the proofs. Now this is our proof for theorem 3.2. So we have six parts of this proof. For the first relation or the first property, that is the reflexive property, again we have A is congruent to A mod M. So how can we prove that? Since um, how do we prove that? A is congruent to A mod M. Okay, this is true because again we're going to have the same old thing. So A minus A, so it's gonna become zero, right? A minus A is gonna become zero. That is M is a factor of zero. Okay, okay, so M is a factor of zero. Okay, so because any number here is a factor of zero. For example, your M is 1,000, so 0 times 1,000 is gonna give us 0. Actually, any number is a factor, has a factor of 0, which wherein if you have a product of 0. So that's for the property 1, the reflexive property. It's proven. For the symmetric property, um, how do we prove that if A is congruent to B mod M and then B is congruent to A mod M? How do we prove that it's true if we're going to interchange the integers? So let's say suppose A is congruent to B mod M. Then we say that M, by the definition of congruence, M is congruent to the difference of A minus B. So that is to say, um, M is M is divisible, M is divisible by negative B minus A. So what we did is just simply reverse the signs and then it will yield us here, this one. So by that, so we say that M is divisible by B minus A, the difference of B minus A. That is to say, I think this is it. B is congruent to A mod M. So symmetric property holds. Okay. For number 3. Anyways, if you haven't seen number 2, the conclusion yet, we have supposed that A congruent to B mod M is true. Therefore, B congruent to A is true. So if that's the case. For number 3, we have the transitive property. Um, so again, transitive property states that if A is congruent to B mod M and B is congruent to C mod M, so therefore A is congruent to C mod M. So let's prove that. Suppose A is congruent to B mod M, and B is congruent to C mod M. Then we say that then M divides A minus B And at the same time, similarly, M also divides B minus C. Okay, so by theorem 3, hopefully you still remember this theorem. Okay, we have first named the theorems in our um, what lesson is that? I think that is in module 2 in the fundamental theorem of arithmetic, the theory of divisibility or divisibility theories. Theorem 3 states something about linear congruences, or rather, not linear congruences. It talks about, no, linear combination, rather, linear combination. So I will give a link to the video above here if you are not familiar with it. So theorem 3, by theorem 3, it stated something like in the linear combination part. So if M is divisible by A minus B and M is divisible by B minus C, so therefore we can say that M is divisible by A minus B plus B minus C. We will just let our alpha and our beta to be 1. So that's acceptable, since alpha and beta are going to be integers anyway. So therefore, we say by this, A minus B plus B minus C, we can clearly see that we can cancel up the B's. Right? Hopefully you see that. So minus B plus B is going to give us a cancel 1. This will be cancelled. And that will further yield us, that this will yield us a M. Okay, where can I write this? M here. M is divisible by A minus C, or M divides A minus C. Okay, so consequently, by giving this out, so therefore we say that A is congruent to C mod M. Okay, C mod M. Okay, we can see it here by since A minus C is our last step. So by the definition of a of a what do you call that, theorem, by theory of congruences. So therefore, this is true. Okay, let's go to the proof of number 4. Number 4 talks about our operations already. So let's put it here, shall we? So this is quite a long theorem to state, but yeah, let's do this. Okay, so now let's proceed to the fourth theorem, fourth part of the theorem. So recall that the fourth, fifth, and sixth part of the theorem are now talking about more on operations, of the fundamental operations, rather than the properties like symmetry and reflexive. So I'm going to read the fourth part again. If A is congruent to B mod M and C is congruent to D mod M, then A plus C is congruent to B plus D mod M, and A times C is congruent to B times C mod M. So let's have a proof of this, shall we? So in the same vein, if we shall say that if um, A is congruent to B mod M, and C is congruent to D mod M, then we are assured, then we can say that um, A minus B um, is, or rather, let's start with this one. We are assured that M is, or M divides A minus B. M divides A minus B, which is in turn, that is, we can say that if this is true, if this is the point that M is a factor of the difference of A minus B, so therefore we can say that A minus B is equal to M times a certain integer k. Let's call that k sub 1. And similarly with our C and D, M is a factor of the difference of C minus D. That is to say, C minus D is equal to M times a certain k. This is a different k. Let's call this k sub 2. Okay. By the way, let's make this clear. This is the equal sign. Okay. Equals. Okay. So if this is the case, so that anyways, the k sub 1 and k sub 2 for some choices of k sub 1, k sub 2 for some k sub 1 and k sub 2. Now what we're going to do is to add these equations. Okay. So we say that by adding these equations, adding these equations, we have, or we obtain, shall we say, we obtain the following. So we will be adding a minus b equals k sub 1 m, and c minus d equals k sub 2 m. So we'll start with that. We're going to add a minus b and c minus d. So what we'll have is a minus b plus c minus d is equal to, we're going to sum this also, k sub 1 m plus k sub 2 m. Now, what we will do is to put together the c and d in this part in the left-hand side and put together the b and d in the right-hand side. So if we'll do that, this will become, let's put this in another line to make it clearer. So this becomes a plus c minus b minus d equals, let's get the common factor here, which is m. Let's make it k sub 1 plus k sub 2 times m. Okay, now next up, we can see that we can fix this left-hand side by getting the common monomial factor. The common monomial factor is just minus 1. So getting that minus 1 from both b and d, we obtain, so a plus c. If you want, we can put that in a parenthesis, minus b plus d, which is equal to k sub 1 plus k sub 2 times m. Okay, now from this equation now, from the last equation that we have here, um, so the congruent statement is indeed true. So from this, let's rewrite this one. We rewrite this one here, the last line. We write this as in the form of a congruence statement. So if we do that, we see here, we can imagine that this here is our A. Okay, this is our A. This is our B. So we are seeing A minus B then is congruent to, this is our certain K. Let's call this K sub n times M. So the thing is, this is an arbitrary integer multiplied by m will yield us a minus b. But in the form of a minus b are binomials. And this k sub n, this random arbitrary integer, is in a form of a binomial. So we're going to fix that notation. Or rather, let's make that notation kind of in a mod, okay, in a congruence relation part. So what do we have? We know that if we're going to put this in congruence relation part, this will become A is congruent to B mod M, right? So um, following this notation, we have the A first. So what do we have? A plus C is congruent to the B is B plus D, B plus D, and then our mod is M, mod M. So therefore, the first part of the fourth statement is true. Okay, the addition part, at least the addition part is true. Okay, now as regards to the second assertion of this property number 4, We can also note that we can note that for the second assertion, okay, let's note that. Okay, so note that um, notice that A times C. Look at A times C, and we will be using the values of A as this: A minus B equals Km. So we will be transposing B to the other side. So A is equal to, if we're going to transpose B to on the other side, what we'll have is um, B B plus K sub 1 M, and then applying the commutativity. That's A. Now, how about C? What's the value of our C here? So C is equal to, rather, C minus D equals K2 times M. So we're going to transpose the D to the other side to make it positive. And then by commutativity, we will have D plus K sub 2M. D, okay, let me fix this. Um, D plus K sub 2M. Now, applying this, using the FOIL method, what we'll have is B times D um, plus B K sub 2M plus, oh, this is quite long, um, inner terms D K sub 1 M, and the last form is, okay, so this is long, K sub 1 K sub 2 M squared. This is 2. Now, notice in the last three terms here, we have an M, an M, and an M here. So let's get the common monomial factor. This is equal to BD plus, you can write it as BK sub 2 plus DK sub 1 plus K sub 1, K sub 2, M. I forgot M, all multiplied by M. All multiplied by M. Now, let's go back in the left-hand side. Oops, sorry. Okay, let's go back in the left-hand side of this equation. Again, we're just only substituting the value of AC. So we can write AC over here so that it can fit the screen. Okay, but simply just to make it fit the screen. So we have AC is equal to BD plus this one. This one is just actually a random arbitrary integer, and then times it to M. Now we want to make it in a congruent statement form. So if we'll do that, what do we have? What we'll have is actually AC is congruent to, because actually we're going to transpose this BD to the other side. So what we have is AC minus BD is equal to BK sub 2 plus DK sub 1 plus K sub 1 K sub 2 M, all times by M. So this is just a random arbitrary integer over here. So we can just think of it as a big integer. And then we'll see here the important notion is here A minus B mod M. Okay, so we can write this as, so our first term is AC. So this can be rewritten as AC is congruent to BD mod M, mod M. So by these two uh, quite long proving statements, A times C is congruent to B times D mod M, and also we have proven that A plus C, okay, here A plus C is congruent to B plus D mod M. So meaning property form 4 has been proven. Now for number 5, let's put it here. We have no more space. Okay, for number 5, okay, Recall our number 5 property. This is still in the proof. Number 5 is if A is going to be mod M, and then we say that A plus C is congruent to B plus C mod M, and A times C is congruent to B times C mod M. So actually, the proof of number 5 is covered by number 4. Okay, so this is trivial. Let's just state it. The proof of number 5, the proof of 5 is covered in 4. It's covered in 4. And the fact you can see that, and the fact that we can see that C is congruent to C mod M. So meaning we can just add M. Okay, we can just think of another congruence statement or congruence relation that tells us C is congruent to C mod M. That is a trivial statement, and then we are sure that this is indeed congruent. So if we're going to put that as a pair to our first statement, A is congruent to B mod M, so we can have the proof of number 5, and we don't need to show it here. For number 6, what is number 6? Number 6 tells us that if A is congruent to B mod M, then A raised to K is congruent to B raised to K mod M for some positive integer K. So we obtain property 6 for the proof by making an making induction argument. So we're going to prove this prove by induction, or if you want by PMI, by PMI. So the statement certainly holds for k equals 1. So for the basic step, or basic step in some books, for the basic step, um, let k be equal to 1. So what do we have? Um, what do we have here? So if k is equal to 1, so what we have is a raised to 1 is congruent to b raised to 1 mod m. So this is just simply um, a is congruent to b. So that's indeed true. Now we will assume it is true for some fixed k. So induction step, assume this is true, assume it is true for some fixed k, for some fixed k. Okay, so from 4, going back in our proof in 4, from 4, we can see that, or we know that A congruent to B mod M and A raised to K congruent to B raised to K mod M together, if we're going to multiply them, together imply that, so by multiplying, we know that A times C is congruent to B times D mod M by our property 4. So if we're going to multiply them, this becomes A times A sub A raised to K is congruent to B times B raised to K mod M. Or equivalently, this is just equivalent to A raised to K plus 1, right? So we have A times A sub raised to K. So this becomes A raised to K plus 1 is equivalent to B raised to K plus 1. Okay, mod M. This is the form of the statement should take the k plus one, and so since we so since the form of the statement took the k plus one form, so therefore the induction step is complete. Okay, so the induction step is complete. Induction step is complete. Okay, so by the proofs in 1, 2, 3, 4, 5, and 6 in theorem 3.2, we therefore say that the whole proof, the whole theorem is true. Okay, that the properties indeed hold. Okay, that the properties indeed hold. Okay, so that's it for the proof of theorem 3.2. Let's show some examples then, maybe in the next video, so that we can separate the examples from the proof of the theorem and the theorem proper. So yeah, that's it for this video. Quite a long video, but we managed. Okay, thank you very much for watching, and I hope you would like and subscribe to my channel. Okay, so thank you very much.